right, for those of you who are interested, I would like to take the opportunity to explain in a little bit more detail this whole process about the particles speeding up versus slowing down, taking the absolute value of the velocity function to get the speed function. And why can I just look at the signs of the velocity and the acceleration? Why does that tell me whether or not our function, our speed function, I should say, is speeding up or slowing down? So it has to do with a small little trick involved in taking the derivative of an absolute value function. So let's say that we have a function which we will define as our velocity function, v of t. Okay, and then I have to take its absolute value in order to find the speed function. That's a t. That's the speed function. Okay, and now what I want to do is I want to take its derivative. Because, like, if I wanted to see if this particular speed function is increasing or decreasing, we take its derivative and we see if it's positive or negative. We're not taking the derivative of the velocity, we're taking the derivative of this absolute value function, and that's not something that we commonly do. So here's the trick involved. The trick involved is the fact that, hey, remember that if we take the square root of x squared, we get actually the absolute value of x. The reason why is because in the process of squaring this, we neutered it. We took away its sign. For example, if I were to stick in -3 and square it, and then take the square root of that thing, I get +3 back, not my original -3. So they're not true inverses of each other. They're kind of like quasi-inverses of each other. Okay, so that's the trick involved here. If I want to find the derivative with respect to t of the absolute value of v of t dt, this is going to be the same thing as finding the derivative of the square root of our velocity function squared. Okay, and then I'm going to rewrite that square root as a rational exponent, and then we're going to just use the chain rule a couple of times in order to find its derivative. So it's like this. I've got the velocity function inside here, which we're squaring, and then we're going to raise that to the 1/2 power. And now I'm going to use the chain rule on this. So, oops, indicates some chain rule. And the reason why I got to do chain rules is because there's stuff inside of the 1/2. And then we're going to have to do it again because the velocity function is also squared. It's like a double chain rule here. Okay. So on the first step, I'm going to leapfrog the 1/2 down, and then it should be times this velocity function squared to the -1/2 power times the derivative with respect to t of the stuff that's on the inside, which is that v of t squared. Okay, so I still need to do that second part, the chain rule part, but in order to do the derivative of that interior, it's again another chain rule. Okay, so let's keep going. I'll bring this other stuff down to the -1/2, and then I'll have to leapfrog this 2 down again, so I'll have 2 times my velocity function, subtract 1 from that exponent, just get 1, and then chain rule tells me that I've got to take the derivative of the inside part, which is v prime of t. All right, and now I'm just going to rewrite some stuff, and notice, of course, that our 1/2 and the 2 cancels each other out. And because we've got a negative exponent on this part, I'm going to put that down to the bottom. And then the other thing that I'm going to do is this v prime of t. That's, of course, the same thing as the absolute value. Let me back that up. It's the same thing as the acceleration function. Okay, which means on top, I've got the velocity function times the acceleration function over this v of t squared to the 1/2 power. So remember how we defined this right up here. the square root of the velocity function squared is the same thing as the absolute value of the velocity function, which is our speed function. So I'm going to rewrite it one more time. V of t times a of t over the absolute value of t. So this is the derivative of the speed function. If I want to see whether or not this is increasing or decreasing, we just check its sign. Well, notice that in this particular fraction here, the only thing that's affecting the sign, whether it's positive or negative, is the top, because the bottom down here's absolute value is always positive, so we don't care about it. The only thing that is affecting it is the top part of it, which is the velocity times the acceleration. So when those two things have the same sign, I look at the velocity, I look at the acceleration. When they have the exact same sign, positive times positive or negative times negative, we've got plus times plus or negative times negative, then that whole fraction is going to be positive, indicating that our speed is increasing. If they are different signs, one of them is positive and the other one's negative, or negative times the positive, of course, then that whole thing is going to result in a negative speed derivative, which means that our speed is decreasing. Which is why, all of this to show you definitively, mathematically, why all we have to do in order to see whether or not our speed is increasing or decreasing is look at the signs of the velocity and the acceleration. When they are the same, it's speeding up, it's hitting the gas pedal. When they are different signs, then it's slowing down. They're working against each other, it's hitting the brakes.